Here we will discuss Safety Augmented Value Estimation from Demonstrations, or SAVED for short, a safe, deep model-based RL algorithm for sparse cost robotic tasks. Reinforcement learning is a popular approach for policy optimization that has seen a lot of success in a variety of robotics domains. However, to learn new tasks, reinforcement learning agents must efficiently explore the state space, which can lead to unsafe behaviors during learning, that lead to constraint violations and inefficiencies. In this paper, we study how exploration can be constrained to regions of the state space with high probability of task success and constraint satisfaction. A common challenge with reinforcement learning is sample efficiency. While RL has seen a lot of success in real-world domains, it can often require a long time or many robots to generate sufficiently many samples for learning. Thus, we will discuss the following questions. Can we use previous task successes to guide the agent's exploration toward regions where task completion is promising? Can we use demonstrations to guide us initially and then outperform them? And can we leverage model-based planning to avoid unsafe regions of the state space by reasoning about dynamical uncertainty? The key motivation for SAVED is to enable efficient policy learning from an initial set of suboptimal demonstrations while satisfying user-specified constraints. We focus on this setting because suboptimal demonstrations are often easier to specify than tuning a dense cost function for a variety of tasks. Misshaped cost functions can lead to unintended behaviors and can cause serious damage to both the robot and its surroundings in safety-critical tasks. Specifically, SAVED is designed with the following objective. How do we enable efficient policy learning with unknown dynamics without violating user-specified constraints when only sparse cost feedback is available? First, let's discuss the problem setting. We consider iterative tasks where the agent must navigate from a fixed start set to a fixed goal set while iteratively estimating system dynamics which are initially unknown. We assume access to a small set of suboptimal but successful demonstrations to initially seed the agent's policy, which can be provided kinesthetically or via teleoperation by a human, or by tuning a PID controller. Hand designing expressive cost functions can be challenging and lead to suboptimal behaviors. We therefore consider cost functions that only indicate whether the agent is in the goal set or not. However, this makes the exploration problem extremely challenging as the agent only receives feedback when the task is completed. Finally, we aim to constrain the agent from entering unsafe states which can lead to damage to the robot or its surroundings during learning. We consider potentially non-convex user-specified state space constraints that must be satisfied during learning. Specifically, we require an indicator function that expresses whether an input state is constraint satisfying. SAVED uses Model Predictive Control, or MPC, which plans over a receding horizon of actions and executes the first action in the best action sequence found. Recent work by Chua et al. Uses probabilistic ensembles of neural networks to iteratively approximate the system dynamics on policy for MPC. The probabilistic ensembles also estimate the uncertainty in the dynamics due to lack of experience or system stochasticity by learning deep ensembles of conditional Gaussian distributions. In this work, we use the uncertainty estimates from probabilistic ensembles to constrain exploration away from unsafe or uncertain regions. Because we consider sparse feedback environments where the only supervision is provided when tasks are completed, we augment the MPC planning cost for a finite horizon trajectory with a value function that estimates the cost to go of a given state under the current policy. This enables the MPC optimizer to reason about the delayed task costs, even though it only plans over a relatively short horizon. We approximate this value function with a probabilistic ensemble of neural networks. Initially, this function is estimated from demonstration data, but it is updated iteratively on trajectories generated by the agent during learning. To constrain exploration in a task-driven manner, we draw inspiration from recent theory and algorithms in the model predictive control community. In learning model predictive control, Rosalia et al. Define a safe set that contains states from which the agent has successfully completed the task in the past. Safety, convergence, and iterative improvement guarantees can be provided in a variety of settings as long as the agent can robustly plan back to the safe set by the terminal state in the MPC planning horizon. We implement a version of this safe set and planning constraint in SAVED. The safe set is defined as the set of states from which the task was successfully completed in prior iterations, including states from the initial suboptimal demonstrations. We simply require that the last state in the planning horizon land back in the safe set. However, this may not be robustly possible in stochastic continuous control environments. So, we fit a continuous approximation to the safe set called the safety density model, which estimates the probability of task completion under the current policy. We now require that terminal states have sufficient density under this model instead. Note that this constraint still allows the agent to explore outside the safe set as in this figure, as long as it can find a sequence of controls that will robustly take it back to the safe set. In this figure, the agent considers three plans at x sub t. The first one is unsafe, as it doesn't end up back in a region with high density under the SDM. The other two are both safe, as their last states have sufficient density under the SDM. In our experiments, we use a nearest neighbors approach to approximate this density. As the agent generates successful trajectories, we add them to the training dataset for the SDM, allowing the set of saved states to naturally expand as the agent gains experience. This enables saved to iteratively improve until convergence. So far, we have discussed how saved handles sparse cost by fitting a value function that is used as a terminal cost in the MPC planning problem. We've also discussed how saved has a terminal state constraint that requires the last state in the plan to robustly fall in a region with sufficient probability of task completion. Now we will discuss how this constraint and user-specified chance constraints are enforced by leveraging model uncertainty estimates. We assume that the user provides an indicator function which tells us whether a given state is constraint violating. Then, we leverage the stochasticity of the learned dynamics model to repeatedly simulate a trajectory induced by a candidate action sequence, determine how often this leads to a collision, and discard action sequences with collision probability greater than some threshold. In the example here, we simulated a length 3 action sequence 4 times and find that it leads to a collision in 3 out of 4 simulations, indicating that it is likely to lead to unsafe behavior. The exploration constraint is enforced similarly. Now we have the full saved optimization problem with the standard MPC objective with an appended value function and 2 new safety constraints to structure exploration based on prior successful trajectories while ensuring controller feasibility. To summarize the algorithm, the user specifies the task by providing the agent with a set of suboptimal demonstrations, a goal set in state space, and an indicator function which defines the feasible state space. The value function, dynamics model, and safety density model are first initialized using transitions from demonstrations. We then solve the saved MPC problem at each time step to execute the policy in the environment and update the dynamics value function and safety density model using data collected from policy rollouts. To evaluate saved experimentally, we investigate whether saved is able to learn how to do tasks more efficiently than demonstrations, consistently complete tasks during learning, and satisfy user-specified constraints during learning. We also compare saved to a model-based RL baseline and 2 model-free RL baselines, all provided with the same demonstrations, in order to evaluate the relative quality of saved's policy. Model-based baselines use the same constraint enforcement mechanism as saved, while model-free baselines enforce constraints with a penalty on the task reward function. We first consider 4 point mass navigation domains to study saved's ability to handle different styles of task constraints. Here, the agent must navigate from a fixed start state to a goal set in a linear dynamical system with Gaussian noise. We first consider a setting without constraints, then add a large obstacle between the start and the goal, then cut a channel in the obstacle to investigate whether alternate paths can be discovered, and then make the obstacle more difficult to force the agent to learn more complex policies. We find that the agent is able to consistently satisfy constraints while accomplishing all tasks significantly more often during learning than baselines, most of which are never able to perform the task in the first 100 iterations. We also find that saved is able to learn more efficiently than all baselines that use sparse costs. We also introduce an Oracle model-based RL baseline, which is provided with dense quadratic costs, and find that this baseline outperforms saved on tasks 1 and 3, but is unable to efficiently solve tasks 2 and 4. This is because tasks 1 and 3 have constraint structures which make quadratic costs both accurate and easy to optimize. This highlights an interesting failure case of saved in task 3, in which the dense cost baseline actually achieves significantly better performance because saved is unable to find the path through the channel while still safely exploring away from the initial demonstrations. Please refer to the paper for further simulation experiments on robotic reaching and pick-and-place tasks. We then evaluate saved on a not-tying task on a real surgical robot with inefficient human demonstrations, which are illustrated in red in the trajectory plot. Note that these demonstrations are axis-aligned and easy for a human to define, but are as a result somewhat inefficient. We specify the not-tying task by enforcing that the policy stay within a 1 cm tube of the mean demonstration trajectory while reaching the mean endpoint. Saved's learned trajectory is illustrated in blue in the trajectory plot, and we find that saved successfully smooths and optimizes the demonstration trajectories. Results suggest that saved is able to rapidly achieve good performance on the task while consistently satisfying constraints during learning, while baselines make very little progress in the first 50 training iterations. In a follow-up paper to appear at Wafer 2020, we establish formal guarantees for saved and generalize it to the multi-start state, multi-goal set setting. We are also exploring different exploration objectives to allow saved to safely expand its safe set to a wide range of start states and goal sets in the state space. In summary, saved is a safe RL algorithm which leverages suboptimal demonstrations to learn efficiently in sparse cost environments while satisfying user-specified constraints. Thank you for watching, and please see our website for more details in addition to the paper, supplementary material, and open source code to experiment with.